All right. Let's see here. Last class, we were talking about the traveling salesperson problem.
Mm-hmm.
And Dicey, you had mentioned that it says, well, this looks a lot like solving, a GPS problem. Like, how do I get from point A to point B? And you were absolutely correct. And that's actually what we're going to talk about today. Because that is a natural extension to the traveling salesperson problem. The traveling salesperson problem is actually a little bit simpler because you're only worried about a couple of key points and how do I get to those key points. With a when I'm trying to find a GPS route from point A to point B, or whether it's GPS or just any type of mapping software, a problem I have just out of this is I'm going to probably have to go through several intersections. I can think of those as vertices, and I may or may not need to make a turn onto a different road. I may or may not need to change roads in order to get to my destination. The number of times that I pull up my GPS to go, how do I get to some places on the same road that I'm on right now, is none. I know where that end of the line is. So how do I get from point A to point B becomes very complicated because I'm going to be making a bunch of different turns potentially. And I don't have a series that I have to go through, which actually adds complexity to my problem. And I've got some other factors I have to look into. So if you've ever gone in, and if you haven't, this is a fun thing to kind of do, because I have a strange definition of the word fun. But if you try like Google Maps and your GPS, if you got a separate GPS device for your car, if you try things like MapQuest and Bing Maps, and just pick a couple different ones. Say, how do I get from point A to point B? You might get 2 or 3 or as many different devices you have, and different answers, because there are certain assumptions that they have to look at with their data set as far as how's it going to work. And so finding out what the best path is becomes very, very relative. Now, sometimes these things are things that you can change. So, for example, in my GPS that I have for my car, I can say, I don't want to take toll roads, but I do want to take interstates. Okay, and I can set that as a priority. Sometimes those assumptions are made for you, and you don't get to kind of choose. So, think about all the different things that might define what a best route to take is. Obviously the big thing is toll roads. We don't have them up here in Tennessee. At least I haven't found one yet in Tennessee. I hope we don't. When I lived down when I lived in Central Florida, every other road you went on was a toll road. It seemed like you almost can't get from point A to point B without going on one or more toll roads, and that was a real, problem if you didn't have cash to go do that, and they moved to electronic cash devices. Um, but so how do you avoid those, and should that be an option? Some people don't like driving on the interstate. They don't like driving next to semi trucks that are doing 80 miles an hour. And that freaks them out, and so therefore they're going to pick non-interstate roads. And other people are like, no, I don't want any rural roads, avoid those. I only want to take the absolute fastest path, or bypass scenic pathways. I remember one time, my GPS, this is an older GPS I had, it took me on a scenic pathway for like 3 or 4 miles, because it was a shorter path, but because it was a scenic highway, the maximum speed was like 30 miles an hour, so it was not the fastest path. And so, do I want fastest, or do I want shortest? Do I, as something like Google Maps or Wave or something like that, am I looking at things like, what's the current traffic patterns? Because if I'm looking at traffic patterns at 11 o'clock at night, trying to make my plan for next morning, and I got to drive it at 8:30, 9 o'clock in the morning, it's going to be a very different set of driving conditions potentially. Um, around here in a smaller town, it's not that big a deal. But if you are in a bigger town, um, once again, where I came from in Central Florida, we had roads that, you know, they might be 55 miles an hour, 65 miles an hour. During rush hour, they were 30 miles an hour if you were lucky. And it's just because of the amount of traffic that they got, and the fact you put that many cars on the road, there was always an accident or two, or multi-car accidents, or car fire, just because someone had an old car and it caught fire, and that slows down traffic. um, and so you had a huge disparity in the amount of time that it might take. And so are you looking at shortest or fastest average, or fastest at this time? Uh, and so how you define, like I said, the best route starts to become pretty complicated. So you have to look at all those different options and how they're going to be uh, applied to the environment. Um, the other thing that you have to wind up looking at when you're looking at something like this is, remember we talked about the traveling salesperson was a infactorial application. And just as a quick reminder, we'll bring this back up. um, if I had five nodes, 5 factorial is 120 possible combinations to go through. Well, if I had 12, it automatically puts me at what, just under 500 million. Um, no one wants to wait for you to calculate 500 million possible combinations. So what can you possibly do? And because a road that only, a road system only has 120 nodes, or possible intersections, if you think of each intersection as a vertice, um, that becomes a pretty small town if you think about it. If you look at Knoxville, which is not a huge town, it's big for this area, but it's not huge. It's probably got thousands of intersections. So how do you work through this? So let's talk about a couple things that it can do. One of the things we have to keep track of is obviously what roads and intersections have we gone through, because we don't want to go through them again. And so if I start going down a path and I see myself like, wait a second, I'm going to go down this path again, I need to stop checking. And this will keep me from hitting additional, or where I have like a loop where I have road road 1, road 2, road 3, road 4, back to road 1. We don't want to get stuck in this loop. That was actually a real common problem that early AI systems had when they would do something called maze finding, when they would try to calculate how to get out of a maze. We're just going to make right-hand turns every time we get a turn. If we can go right, we'll go right. And you would find them just going in a circle. And so if we keep track of where we've been, then we know how not to get stuck. And that's one exit criteria. The other exit criteria that we can use is, once I've found a method, then I'm going to once I find a method that's longer, I'm obviously not a better route, and I'm going to exit out. And so now I might have 500,000 different options, but most of those are going to quickly fall away. Go, okay, these are not options I'm going to take. So I'm going to back out, and I'm going to keep, I might start down that path, but I'm not going to go the whole way. So out I go. And that's going to make that number that you see there, that 500,000 number on the screen, or 12 billion, or whatever that number winds up being, that's going to make that number get a lot smaller and be a lot more efficient with us. The other thing that we have to just kind of realize is that sometimes we're good enough. And there's a whole process and a thought of um, best versus good enough. And there's actually a book out there, if I remember correctly, called um, "Great is the Enemy of Good," I think is what it's called. And it was talking about how you could keep working trying to find the best and go through every possible combination. The problem is the person who needed it no longer needs it because they died of old age. Um, and that's not relevant to you. But if we can find something that's good enough and we can say, hey, we've tested, 50 options and this is the best one, I'm going to call it done. I'm going to say, you know what, this is good enough. We are done, and let's move us out of here. And so there's a lot of different ways that we can work through that process. This actually started off. There was a research paper that was done watching firefighters, and I put this in here, and it's also in the online book if you're interested. Um, but these researchers said, firefighters, they've got to make decisions very quickly and they've got to always be right. If they're wrong, literally lives are at stake. And so they said, we're going to watch firefighters because they are probably the best at making the best decisions as quick as possible. And so they started watching them, and then they'd have like these after action reports, and they'd say, okay, why did you do X, Y, and Z? Or why did you do this step? And the firefighters turned out didn't care about the best option. They would find an option that would work, and as soon as they identified an option that would work, they used that one. And they didn't have time to start thinking about every possible scenario or combination or hidden uh, thing that they may not know about. They had to use speed was the most important thing to them because the fire's not paused, it's obviously burning. And lives are literally at risk, theirs and possibly people inside the building or buildings next to them. And so they didn't look at the they didn't look for the best option. If they got the best option, great, but they didn't look for it. They looked for what could they determine based upon what they saw, what they could evaluate, and as soon as they found something they were confident would work, they went after that one. And so being able to say, hey, we're going to stop this, we're going to end our testing so you can start driving or you can start going on the road or you can print out results or whatever that option is. um, Knowing when to stop is a very important thing, and whether we use some hard-coded thing, hey, we're only going to check for 50 iterations, or uh, we're just going to the first one that we find, because we're going to use some heuristical models, we're always moving towards our goal, never away from it. um, However that decision's made, there's a lot of ways to make that decision. However that decision's made, that's a very important thing that we can bring into not only this problem but other problems that we might have going forward. um, if you think about it, if we go back to like our old sorting algorithm problems, and we looked at several different ones, and you said, well, I could write this as a bubble sort, I could write this as a selection sort, and then a heap sort, and then a quick sort, and then okay, and then I'll figure out after I write all these and run them, I'll figure out which is the best. How much time and effort was wasted in spending on something like that? So knowing how to pick a good enough instance, a good enough application, is a really important thing that's been run. How you determine what's good enough, that's really situation dependent. Um, because a lot of it depends upon your problem set and what you're trying to solve and work through. Um, so those are all considerations that you have to make, and you need to start thinking about as you get into larger and larger data sets. Now, the good news is if you were doing something like this with graph theory, like I said last class, we're talking about a really small subset. I'm taking a subset of all computer science, and I'm giving you like the 30,000 foot overview. When you start getting into into the weeds, there's answers to some of these questions. There's algorithms that you can pick that are specific, that are going to use that essentially a divide and conquer type method to eliminate vast majorities of the options. So instead of having 500 million possible combinations, you're only looking at a million, and that type of stuff, which is a huge drastic reduction. In fact, there's a whole process called uh, graph reducing that is all about that. And how do I not have millions and hundreds and millions and billions of possible combinations? So understand that there are ways to make this decision intelligently, but there is that question that always needs to be asked and put into effect whenever we're working with something. This is just a really good example, because if you think about how many possible edges and vertices and stuff like that you would have for something that looks like a city map, um, it creates some really interesting problems and ways to go about solving it. We've done a pretty good job with it. But we always come up with different ones. And a perfect example of coming up with a different way of looking at information is, if you guys have looked at Google bought them. It was actually I believe it was an Israeli company that originally created it, called Waves. Waze, W-A-Z-E, I think is how you spell it. Um, that information was really interesting because it used crowdsourced information, as far as everyone who had the app was sending information back to the server and says, this is where I am, this is how fast I'm traveling. And they could figure out, oh, you're on a road, oh, you're doing 30 miles an hour, you're supposed to be doing 50 miles an hour, this road's a slowdown. Well, they could take that information and extrapolate additional piece of information and follow that some people get on a certain pathway to go from point A to point B. And so if I use a crowdsourced type of information, I can watch where everyone's traveling and stuff. Now, I might notice that, hey, to get from point A to point B, the point A sometimes changes, the point B sometimes changes, but there's this middle section. And this middle section is used by lots and lots of people, and we're going to determine it's the best way. We're going to assume, and this is called the wisdom of the crowds. It's actually a term whenever we talk about crowdsourcing information. We assume that people in general are really smart. Um, Individuals might not be so smart, but if I look at 10,000 people doing something, oh, well, if 10,000 people are doing it, it's probably the best way to do it. And so I can find certain corridors to say, oh, I don't have to check all these possible combinations. All I need to do is get to one of these commonly traveled corridors, and then I can direct you. And so that makes kind of a really interesting combination of using crowdsourcing data, known data sets, and a variety of other things to simplify that problem. And that's a completely different way than necessarily finding a pure algorithmic approach. A pure algorithmic approach might find a different solution that's 30 seconds faster. But is it worth it? How much computing time is worth it to save 30 seconds for a single individual? Now, if we're solving this problem for tens of thousands of people that occurs every day, that's a different story. But those are all things we have to make in consideration. So, can I find crowdsourced information that help me direct common pathways that lots of people use, and then I can just start connecting these common ways to get. And so my starting point might be different, but everyone's got to go to the mall. How do most people come into the mall, or how do most people go into this town or that town or something like that, and figure out that way to simplify my process? So it creates some interesting ideas, and there's still, even though these type problems have been around, traveling salesperson, I think, started in the 60s of all things. Um, possibly before that. Even though these problems have been around for a long time as far as computer science is concerned, there's still some interesting ways of how we can approach solving them using completely out of the box different type of thinking that wasn't available to us 10 years ago. 10 years ago, the number of people who had smartphones that had GPS turned on or GPS in their phone at all was relatively small. So we need to always be looking for other ways to potentially look at solving these types of problems when we go forward. Okay. Any questions on that part of what we were talking about as far as finding a best router, some different techniques that we're using as far as that goes? That was really, it's a continuation of where we were last class, but it's a interesting subset of that problem, if you would. No questions? Okay. Okay. Next week, we're going to start talking about something called a Tower of Hanoi. Actually has a couple different names attached to it. Interesting problem because it's a recursion problem, and it is a also it's a very nasty algorithm as far as how many steps it takes to do something. But it's a pretty easy one to implement and stuff. So we're going to work on that next class, and we will have that as an assignment in preparation for working for a review of our next test that will be coming up the following week. After that, we'll start moving in, working on JSON data and XML data and how we can work with that, give us some experience handling that, and moving some other things forward as far as that goes. From there, we'll look at how do we calculate how strong a password is. It's a pretty easy one, but it shows you how we can use some simple math to figure out some stuff. Might show some other complexity ideas and why we use stuff like that. And then we'll do regular expressions. Has anyone had any experience with regular expressions? I need to know because I need to know how complicated to make that.
No.
No experience with that.
Okay. Well, you've heard of Dante's 7 levels of hell?
Yeah.
Regular expressions is sometimes assumed to be level 8. It's you're going to look at it and you're either going to love it or you're going to hate it. I can't tell you which because it seems to vary by person. The amount of things that you can do, the complexity of what you can do with it is really, really cool. I've done all types of really weird stuff. I got to see if I can dig out some old examples of ways I've used regular expressions. And they're really interesting, but you've got to be careful with them, as you can just throw yourself in a weed so fast. But we'll look at that, and then we'll be getting close to being done for the term, which I'm sure you guys are excited for because last term, I know about this time I was just could not wait to get done with school when I was a senior in your guys' place.
Yeah.
So it'll get there before we realize it. So anyway, I do want to just, I'll stick around for a little bit if you guys have any questions about things going forward. Otherwise, I'm good with today. But if you do have questions about, graphs in general, or a specific part maybe we talked about last class you want to talk about, we can separate that. Otherwise, you guys are free to go and get some lunch and whatnot if you haven't had lunch. And we'll talk on Tuesday. Yeah, Tuesday.
Monday.
Monday. Yes, I'm sorry. I thought I was doing so good. I was so close. No, Monday. We'll meet again on
You
Monday.
almost had a perfect class.
I almost. Well, the problem is if I have a perfect class, then everyone's going to assume that every class I'll just keep on being perfect, and I can't have that. I have to throw something, you know.
Have some variety. Some variety.
I was making sure you guys were paying attention. That's what I was doing. Yeah. That's what we'll call it.
All right, bet.
All right. If you guys want to stick around, like I said, you're more than welcome to. Denise and Kate, I have some information for you on the other class if you want to stick around now and so we'll talk about it then. Otherwise, have a great rest of your day.
Also,
Yes.
I'll email you to set up a time to meet tomorrow.
Okay.
Over video.
Okay. Yeah, for the other assignment thing. Gotcha.
Yeah.
Sounds
All right,
great.
I'll talk to you later.
All right. Talk to y'all later. Let me